Okay, so thanks everyone for coming. So I'm going to talk about new tricks for expander codes. And so I'm going to talk about two recent papers, which sort of the union of the authors is here. So joint work with Brett Hemingway and Rafi Ostrovsky. Okay, so let me give you the one-slide version of the talk, because we're getting started a little late, and I'm right between you and lunch, so it's you can see the one-slide version and then sneak out, and I won't be offended. So here's the one-slide version. So I'll define expander codes in a little bit, but basically you can make an expander code out of some inner code and an expander graph. And expander codes have been around for a while, since the 90s, and there's been a long and beautiful line of work sort of exploring them, starting with Sipser and Spielman and other work by Barg and Zamor. And the basic punchline of this line of work is right here. So if the inner code has decent distance, then your expander code has decent distance, and it's decodable in linear time. So it admits a very fast decoding algorithm.
Why would they like an expanded code to begin with? Why would they like an expanded code to begin with?
Why would you like them?
Yeah.
Oh, because they have very fast decoding algorithms. Yeah, so that's why they were originally introduced, is this punchline. So linear time decoding algorithms was their original selling point. But today I'll give you a few more selling points. So this talk extends this sort of thing more generally. So the moral that I want to get across is that if the inner code has decent something something, then so does the expander code, and there's an efficient decoding algorithm. So that's the high level point. And the two examples that I'll give are one about locally correcting codes, so I'll show that if the inner code has decent locality, and I need to define decent, then so does the expander code, and it's locally decodable, actually locally correctable. Which is to say, I can actually correct it in sublinear time, so that's efficient. And the next example is that if the inner code has decent list recoverability, which I will also define in a minute, then so does the expander code, and it's list recoverable in linear time. So those are my two punchlines. So let me give a brief overview of what that means and the types of results we get, and I'll sort of zoom in detail as the talk goes along. But so here's a slightly less zoomed out version. So what we can get for locally correctable codes for expander codes. So local correction, very briefly, means that I can correct one symbol by looking at just a few other symbols. And so we've heard a lot about local recoverability, like in the last talk. This model is a little bit different because there are errors. So it's a harder model. And what we get in this harder model is codes with rate going to 1, and the number of queries you need to make, the locality, is n to the epsilon, where n is the block length of the code. So it's smaller than n. And the other thing I'm going to talk about is list recoverable codes. So list recoverability, very briefly, means that instead of errors, I have some sort of uncertainty. And I'll quantify that more in a bit. And what we get here is codes with, again, high rate codes, rate tending to 1, and with a linear time recovery is the punchline. And one reason that it's nice to get codes with both of these things, with rate tending to 1, is that we can plug them into an approach of Mir. And so he has kind of a similar sort of moral theorem to the one that I gave on the previous slide. So his moral theorem is that given codes with something or other in high rate, then you can get codes with something or other that approach the singleton bound, using a very nice construction, actually originally sort of modified from one of Alon and Luby. And so when we plug these sorts of results into this machinery, we get sort of results with sort of the optimal rate-error trade-off in both of these models. So that's a broad overview.
Are the new codes over a larger field?
No. So whatever the field sizes of the inner code, or whatever the alphabet sizes of the inner code, the outer code has the same alphabet. Oh, sorry. After I run them through this, yes, they do have a larger alphabet size. Yeah, as they must, if they're going to be. Yeah. Okay. So that's a very high-level overview. Now I want to get back to your question, which is why should we care? Okay. So here's some of the selling points, with all the flashy colors from why we might care about some of those previous results. So with locally correctable codes, This gives a sublinear time decoding of expander codes. It also gives a new construction of high-rate LCCs. So we knew how to get these before. There's been a couple constructions known, but this is a new and different construction of those. For the list-recoverable codes, these trade-offs, we actually didn't know how to get them before with linear time recovery, so this is something new. List-recoverable codes are sort of interesting in their own right. They're also related to other problems, like they're very related to list decoding. Many list decoding algorithms are secretly list recovery algorithms. They're also recently have been used in group testing compressed sensing algorithms. So they've been useful there. One caveat is that our error model is a little bit different than the ones that are useful in this regime, so we can't immediately.
When you talk about sublinear, you're thinking of that you just want to figure out one bit.
Exactly. Yeah. Another reason you might care, which I think is maybe more important than these, is this general moral. So, like I said in my 5-minute talk, 3 examples will make a theorem. So now I have 3 examples of start with inner code with decent blog, get an expander code with efficient, the same thing. So I hope that there are more examples in this regime. But the main reason that I'm talking about this problem in this audience, from theory to practice thing, is that I think why do we care is still largely an open problem. And so this is what I want to ask you guys. Here's a bunch of reasons why I might care, but I think that there are lots of other reasons why we could care that I don't know yet. And so in particular, I'm interested in sort of what are other things that I can fit into this sort of folk theorem. We've heard of lots of desiderata that we might like from codes, which are maybe not so standard. So far in this workshop, local recovery and lots of other things that are useful in practice. And I'm wondering if there's anything there that could help here. Also, more concretely, like I said, this error model isn't immediately useful for the applications that I know of for list recovery, but maybe there are applications that you know of where it is useful, and in that case, I'd love to hear it too. So we heard a couple of compelling talks earlier about why an erasure-like model is useful, and that's what I'm going to be talking about here. Yeah?
To get these optimal trade-offs, what kinds of expander graphs would you need?
Which optimal trade-offs?
Or
So we use Ramanujan graph, and we have explicit ones of those. Yeah, so these are all completely explicit constructions. Yeah.
So I have a quick question. So for Ramanujan graphs, you can only prove expansion of some amount, right? You can get better expanders, but it's only provable. What is it? An expansion of half? What kind of expansion?
So here I'm talking about spectral expansion, which I'm going to measure in terms of the second eigenvalue of the normalized Laplacian.
Like vertex or edge expansion as well, but there's a gap there, right?
There is, yeah.
It's up to a half. Yeah. So what's surprising is that for some of the old expander graph results, you need actually expansion higher than that. You need 2/3. So for example, like the original, what is it, Citrus Mellon, you can't prove error correction with Ramanujan expanders. You can only prove it with expansion 2/3.
Okay.
So if you might have a different proof of that.
Yeah, so the stuff that we're building on is the version of expander codes that come from Zamor, and so he uses just the spectral expansion, and there it is enough. We can talk more about this offline, but yeah. So all our results are in terms of the spectral expansion, in terms of the second eigenvalue, and we don't need the combinatorial expansion guarantees. We only need the spectral expansion, which we do know how to get explicitly. Yeah. Other questions about why anyone might care? Okay, cool. All right, so now that we all care, let me give you some more details. So first I need to tell you what an expander code is. I'll tell you what a Tanner code is, and then I will tell you what an expander code is, which is a special case of a Tanner code. So a Tanner code is obtained by a graph, a d-regular graph on n vertices, and an inner code, which will have length d. And here we should think of n as going to infinity and d as being something independent of n, like 10, some constant. Right? And from these two ingredients, this d-regular graph and this inner code, we're going to get an expander code, and it's going to have length nd/2, the number of edges in the graph. Okay. And code words are going to be, I'm going to think of them as labelings of edges of my graph. So what constitutes a code word of this Tanner code? So a labeling of the edges of my graph is in my expander code if the labels on each vertex form a code word in the inner code. So that is to say, so here's a labeling. So let's say my alphabet is size 2 here. So I've labeled all the edges of my expander code. And this is a legitimate code word. This labeling corresponds to a code word in the expander code if for every vertex I've sort of ordered the vertices or the edges coming out arbitrarily if those guys form a code word in the inner code. So here I actually worked this out. This is a code word when the inner code is a 743 Hamming code. So if you're bored, you can check that for the rest of my slide. So this is a legit code word. Okay. And it's not hard to see that if the inner code is linear, then so is the expander code. Basically, I had all these linear constraints for my inner code, and now I'm just imposing those constraints sort of locally on the vertices. So now I have a still linear code. And moreover, by counting these constraints, you can figure out the rate. If my rate started at R naught, then my new rate is going to be 2 R naught minus 1. You can work that out. And if G is an expander graph, then I'm going to call this an expander code. And here, if you know about expanders, great. And if not, it's some low degree graph that's very well connected. And like I was saying earlier, we could just take G to be a Ramanujan graph. And we have.
This happens only for bipartite codes, right? Not for any code, not for any graph.
Any deregular graph, this is true.
But the rate might be bigger, right? Because
Yeah, it's
some of
greater
the
than the
constraints
rate.
might.
Yeah. Sorry, with rate at least this. The rate might be bigger, but.
I was worried we get negative rates for small r0.
Yes. So the rate is at least this. It does not go down to -1. Yeah, thanks. And I think, so what you were saying is that often it's the case that for these expander codes, I won't use an expander graph, I'll use the double cover of an expander graph, so some sort of bipartite version. And we can move back and forth between them. For this talk, I'm just going to assume that I just have a non-bipartite version just for ease of figures. But you're right, in the papers we do use a bipartite. Okay. So those are expander codes. Any questions?
Just a comment.
Yes.
These look like codes with locality, right? They seem to have a lot of locality.
Yes.
Because of this.
Indeed. And in fact, I will show you how to take advantage of some of that locality now. So locally correcting expander codes. So now let me give you a brief overview of this. So what do I mean by local correction? So we've seen a couple of models of, what we might want from locality so far, with the local recovery and stuff like that. This is a little different model. So here there are errors. So Alice has some code word that she wants to send to Bob. There it is. Some bad guy introduces some errors adversarially. And now Bob's job, and the bad guy also tells Bob, recover me this symbol. Tell me what that was supposed to be. And Bob's job is now to query a couple of positions and figure out what that symbol should have been. And in this case, he wins. He successfully realizes that it should be an O. Okay. So that's the definition of locally correctable codes. Slightly more formally, we say that a code is Q delta locally correctable if Bob can do this when the adversary gets to introduce a delta fraction of errors, and Bob makes Q queries. And the queries are randomized, and we want him to be able to succeed with high probability over the choice of his. So how can we take advantage of this for expander codes? So here's the theorem we get. This is an informal version. Again, it's just before lunch. I don't want to slam you guys with notation. But morally speaking, this is what we can show. If you have an inner code which has some kind of locality, which I will call non-robust but smooth, which basically means I can reconstruct any symbol in many ways, but I do not need to be able to tolerate errors in this reconstruction. So it's not itself a locally correctable code, but it has some locality. And I take a Ramanujan graph as my expander with large enough degree in terms of all of the parameters that have been floating around. Then the expander code that I get from combining these two ingredients is locally correctable and the number of queries I need is n to the epsilon. Here, I think I haven't defined this. So capital N is the number of edges in my graph, so it's the block length of my code. And delta is the amount of error I can tolerate. And unfortunately, for us, this is rather small, so it's 1 over polycube, but it's some constant, depending on the locality of your original, of your inner code. And we can instantiate this with some particular codes that we get from affine geometries. And the punchline is that we can get codes with rate approaching 1 that are n to the epsilon delta locally correctable. And again, here, delta depends on alpha and epsilon in some polynomial way. And like I said, we can also shove this through this construction of mirror and get codes. And actually, this was his original motivation for this construction, is turning high-rate, locally correctable codes into something like this. You can get sort of the optimal trade-off. So you can get codes that approach the singleton bound, and they're locally correctable up to half the distance. So just a quick lit review here. So getting codes in this regime is not new. We knew of a couple of families of high-rate, locally correctable codes before, but this is a pretty different construction. These guys are all algebraic, and this is really not. So
sorry, this is it from the properties Yekhanin Saraf construction?
Mm-hmm.
The one you're citing, the multiplicity codes. Is this a different result from properties Saraf Yekhanin?
Oh no, I just forgot to write Saraf Yekhanin. I'm sorry, Sergey. That's awkward. I got bored after typing. Can't figure out where the H's go. Okay, sorry. Apologies. No, that is just my fumble. Okay. Sorry. Are there any other questions before I move on? Okay. So now let me move on to linear time list recovery of expander codes. How am I doing for time?
Well, started a little late, so it's between 10 and 15 minutes.
Okay. All right. Well, people can walk out at noon if they feel like it, and I'll just keep going. Okay. So let me talk briefly about this list recovery problem. So the list recovery problem is different. It's a slightly different error model. So before we had this error model where a bad guy gets to introduce errors. Now we have an error model where the bad guy gets to introduce uncertainty. So here's Alice's code word, hello, how are you, is there, but the bad guy has been, or the adversary is able to, or has given some list of possibilities in each position with the guarantee that the intended symbol is in that list. And we can make it life a little harder for Alice and Bob. Maybe there are some positions that we just know nothing about. And now Bob's Bob's goal is to look at these lists, or lack thereof, and try to recover the original code word. In this case, he has to recover a list. He can't recover just the code word itself. Because, what if I took one code word here, one code word here, one code word here? He'd have to have list size at least 3. So Bob's job is to recover a short list, in this case, size 3 or bigger, not too much bigger, that contains the correct code word. So again, more formally, we say that the code is, now there are 3 parameters to keep track of: alpha, little l, and big L list recoverable from erasures. If for any set of lists which have size at most little l, so little l here is 3, there are at most capital L code words, so that would be the size of Bob's list, that agree in all the lists given, and I'm allowed, I need to have lists in an alpha fraction of the position, so 1 minus alpha fraction, I'm allowed to put question marks in. So this is a slightly different definition of list recovery than is often given. It's a little bit weaker model. So that's why I've qualified it list recoverable from erasures. So this is a definition that was given in Guruswamy and Indic, or in some work of Guruswamy and Indic. But there are other error models. I might say that these question marks aren't in fixed locations, but rather I just need to agree with an alpha fraction. So we cannot handle that error model right now. Okay. So is the definition clear? Yeah, and so I should mention the list recoverability is related to, like I said before, list decoding and is useful in a lot of other things. Okay, and so what is our result? So same type of setup. If we have a inner code that is list recoverable from erasures, an expander graph of degree d, which needs to be big enough, then the outer code is also list recoverable from erasures. And we can instantiate this. In this case, we can instantiate with random linear codes to get a trade-off like this. So we get rates tending to 1 and list recovery from erasures with constant list sizes. And again, shoving this through the same construction of or mirror, we get basically the optimal trade-off here. So for any rate, we need lists only in an r plus epsilon position. And you can show that this is optimal. And just again, a brief lit review. So previous linear time constructions had low rate, and previous high rate constructions had superlinear time decoding. So polynomial time, where the exponent on polynomial is like 1 over epsilon or 1 over epsilon squared or something like that. So this is much faster. So this is the first construction to obtain sort of the best of both worlds, linear time constructions with, or linear time recovery with high rate. Okay, so in my remaining 10 minutes or so, I want to give a flavor of the algorithms that are used. So here's how the list recovery algorithm goes. So I'll just give a sketch. So what is the list recovery problem? Again, we have these like lists on each edge. So here's one vertex in my graph, a bunch of edges coming out of it. We have lists on each edge. And I want to figure out I want to find a list of possible code words that are consistent with all the information given. So the first step is just to list recover locally at every vertex. The inner code is locally recoverable, so I can do this. So I get some possible list of code words of the inner code that might belong on these symbols. So now let's do a little thought experiment. Let's suppose that we just decided that this symbol was an A. It could be an A or a B, but let's just say we're going to decide it's an A. Right. So then, well, what do we know? Right? We look at this list. Maybe this is the position that corresponds to that edge. Maybe there are a couple of code words that have an A in them. So now we've narrowed down the number of code words. Okay, so it's either this one or this one. It's not this guy in the middle. Okay, so that's great. But actually, we even have more information than that. If we look at, say, this position here, which corresponds to that edge, we don't know which of these two code words it is, but we do know that for sure that position has a D in it. Right? And similarly, there are probably a bunch of other positions like this also. So the moral of the story is if I decide arbitrarily that this symbol is A, that determines a bunch of other edges. And that's basically the whole algorithm. So I make one decision, that determines some other edges. Making those decisions determines some more edges, and so on. And because this is an expander, we hope this will propagate out pretty fast and cover a lot of the graph, a constant fraction of the graph. Okay. Then we repeat. We make another decision. That will determine some more edges, and so on. And we repeat this a constant number of times until we've covered almost all of the graph, at which point we can correct the rest of the edges using the normal decoding algorithm for expanders. And the number of possibilities that we have at the end of the day is L to the number of these yellow edges. Right? So that's sort of the number of the number of possibilities I had. If I only had to make these decisions, I can make all possible decisions and get a short list. And the length of my list is L to the constant. So that's basically the whole algorithm. And then you have to do some work to show that this actually works. But that's it. And I'll just really quickly give a flavor of the local decoding algorithm, which is super easy because it's exactly the same animation. Right, so let's say I want to know this edge. Now my inner code is locally correctable. So like you were pointing out, they have some locality here. I can use these two edges to determine the symbol that's supposed to go on that edge. And I can use, now I want to know this edge. I can use two more symbols to learn the value that goes on that edge, and so on. And the algorithm is now basically, well, query that tree, more or less. with some caveats. And so that now that's basically it. And you have to show that we can actually reconstruct the value that goes on this edge from this tree, even if there are errors. And this takes a little bit of work, but the basic idea is that suppose that I had two trees, and I'm trying to decide which one is the truth. So I have some error-y version of one of these trees. And this one has a different symbol on the root than this one. Well, then they also must differ in one of the children of the root because of the locality. And then they also must differ down there. So they must differ from an entire path from like the root to the leaf of this tree. And it turns out that that's actually enough to let you deal with errors. If I'm trying to decide which of these two is correct in the presence of errors, you can show that because each of these paths is basically a random walk on an expander, they will probably no errors will sort of aggregate in a nasty way on any path. And it turns out that's enough. And you can make that rigorous. Okay, so those are just the flavors of the ideas. And that's basically the end of my talk. I just wanted to reiterate the moral of the story is that if the inner code has decent something, then so does the expander code. And I hope that you will help me fill in more somethings. And I gave two examples, locality and list recoverability. And there are a bunch of open questions. So one, I think the most interesting, but what other properties can I shove into this? I think it would be very interesting to handle list recovery with errors. So that little caveat that I was saying when I had erasures instead of errors. If we could do errors, then I think that would lead to some definitely improved algorithms for list decoding, compressed sensing. It'd be very cool. Other applications for list recovery with erasures. And also better instantiations of these. So everything that I said was sort of living in asymptopia, and I didn't say what the constants were to this audience because I would be embarrassed. They're quite bad. So actually making these implementable, I think, is a very interesting question. So that's all I have to say. Thanks.